Right. Thank you very much. First, I would really like to thank Michal and Johannes for this lovely workshop. It's been wonderful for a variety of reasons and mostly to reconnect with the tribe. I mean, and this is very nice. As you can observe that there are two speakers already who participate in this meeting, and this work is the work I'm going to present is in collaboration with them. And the basic, the work itself, the people who have done it is Niranjan, Nishant, and Amrendra. And Amrendra is now a postdoc at Orsay with Olivier. Um, Niranjan is with Alain Aspect in Orsay again, and that's where we are. Okay, so without further ado, let me just tell you. So basically, what we want to do is what I have always wanted to do is to explore symmetry and its consequences. And for me, a homonuclear diatomic system, atom ion system, was the perfect system to do it. And for historical reasons, we started with alkali atoms, and that is where we are. And we are moving towards alkaline earth atom ion systems. But so what I'm going to tell you briefly is the experimental platform. Then we are going to talk a little bit about the exchange symmetry between in ion atom collisions and the link between cross sections and the diffusion that an ion would see in a cloud of atoms. Then we talk about charge hopping and how competing diffusion leads to very interesting, possibly observable phenomena. Um, so So, as I said, there are two possibilities. Either the ion and the atom are of different species, and most experiments which happen are with nowadays with lithium, which is a light atom, and a heavy ion. But and lithium is everyone's favorite now because of the mass and the polarizability. It's a great system, and the ion and the atom are of the same species, and this is where we have been for ever since we started doing these experiments, which is 2008 onwards. Okay, so here I want to explore the consequence of this symmetry. And of course, the interaction is this one, which has been flashed many times. So before I just get to this, I want to make people aware that while my talk is mostly theory, we do experiments, and pandemic made us uh, kind of a bit of theoreticians. And so I want to introduce the concept of hybrid trap that we have. And essentially, we have this is one of our hybrid traps, but this is like the hybrid of everything. Let me explain. So you have the vacuum system, you have cavity mirrors, which can actually, you can do quantum optics with this thing, with cold ensembles which are there. You have a cavity piezo, which can change the, excuse me, length of the cavity. You can make cold atoms, you can make multi-species together. You have charged particle detectors, and this is the center of the experiment. You can have, we have two different ion traps which you can do. One is a wire trap, one is with the quadrupole rods, which you can see. And you have the ion trap, the blue or the blue lines or these quadrupole rods can give you the RF, and the red wires can give you the N cap. So we have the prospect in this experiment to trap atoms, ions, molecules, and light. Okay, and we can actually do whichever combination. And now our focus is increasingly towards molecules. And what I would tell you, Rosario, is that RBK, the new experiment, new cavity experiment we built, is an RBK experiment which is built for non-destructive detection of interactions. Okay, so just for, since you brought it up, it's a good thing. So at the end of the, you have cold atoms in the middle, which would be overlap with the cavity mode. And you have trapped ions, which is a bigger volume in our case. And this is all I want to say about this particular experiment. It's a concept, and I want to push it out there. So now let me just, in one slide, go back to a little bit of work that we did. And Johannes and his group has also done something of this in this. So this is what is called swap cooling. And essentially, if you trap ions in this ion trap and you wait for some time in our trap, it decays and we lose the ions as a function of time. Now, if you are talking about cesium ions and with rubidium atoms, what is happening is that your cesium ions are going down in time, which means that there is a certain heating rate, which is uncompensated. Now, you put rubidium in this mixture, you put with the cesium ions, you put rubidium atoms, and you increase the lifetime, which means that there is a cooling interactions which is happening. And there's a lot of detailed work and analysis which has gone. I'm trying to summarize all that in one slide to motivate what is going to happen next. But now, this is the cesium ion with a cesium mott. And you can see that the lifetime has increased much more. There's much more efficient cooling between cesium ions, of cesium ions with cesium atoms. Whereas, actually, it should have been worse than this and this. So this red curve should have been under the gray squares. Okay, if you had the more conventional understanding of various of heating and cooling of ions in trapped ions. So that's where we are. So this got us to wonder, and this was the signal you got when you just put the experiment on. So this got us to wonder that there's something very special happening because the ion and the atom are the same species, and this has to be the consequence of exchange symmetry. So apart from elastic collisions, which is where the rubidium is. So with rubidium, you have only elastic collisions, and this is elastic collisions plus exchange. So now, oh yeah, okay, sorry, I'm lagging. Okay, so what do you mean by exchange? It has been alluded to in this meeting several times. Let's say you have a cold atom at the center of the ion trap, and this is position, this is time. As you, in time, the cold atom is not moving, but now you have a fast ion coming in, they get proximate. The valence electron, the lone valence electron, is shared momentarily between the two cores, which are identical. There's no cost in energy. And therefore, with a 50% probability in such a situation, in a glancing collision, you can move with a fast atom out and a cold ion at the center. So you, in one shot, you have a 50% probability of switching a fast ion to a very cold ion at the center of the ion trap. So this is, I mean, there's a whole bunch of work we have done on this. I don't want to really put that, go for that now. So now, let me get to the thing. So now let's say that the homonuclear ion atom system is a bit special and slightly different from the heteronuclear. So what happens is that you have 4 combinations that are possible if you allow for exchange. This is direct elastic. This is forward scattering without charge exchange. You have backward scattering without charge exchange. This is forward elastic scattering with charge exchange. Okay, in all cases, the theta is what you call the scattering angle if there were no charge exchange. Okay, and this is backward scattering with charge exchange. And this is where, so these are the 4 combinations. And what happens is that then, and I apologize for the quality of the eventual equation which has come out here. I mean, not for the scientific quality, but for the reproduction, sorry. Because anyway, the scientific quality is due to Massey and Smith way back in 1933. And it's so good that we have to resurrect it. So essentially, this is the differential scattering cross-section. Here we have the nuclear spin dependence in terms of x and 1 minus x, where I is the nuclear spin. Okay. For fermions, it's one thing. For bosons, it's another thing. This is for half integer and for integers. So this bosons, fermions. And then you have the scattering, the scattering amplitude from the VG potential. and the scattering amplitude from the VU potential. And this is how the, the this is the correct way of looking at the cross sections, okay, which is very formal. There is 9 decades of theory now which supports this. So this is right from the early days of scattering theory. What is instead very commonly done is this. The differential cross section as a function of theta is decomposed into Fg plus Fu, okay, which is then identified as the direct elastic differential cross section, and then there is the resonant charge exchange differential cross section. So this is how the two are identified, and that's where you get into this thing whether there is elastic cross section, whether the collision is elastic or whether the collision is charge exchanging. And the point is that gives you a very interesting relation, which is that if you go by this formulation, then the elastic scattering is the difference between total and charge exchange scattering, which is a slightly funky when you think in terms of cross sections actually, but it is used. So which is approximate. It breaks down at the very low energies. So for most practical purposes, and I will show you where the validity of this thing breaks down. Okay, so I'm putting question marks across that, so to obliterate that expression. And this is what the total cross-section looks like. The total cross-section is a mess, but it is complete. I mean, once you know the phase shifts, you're done. I mean, and phase shifts we calculate, rho is calculated. Every one of us now knows how to do phase shifts very well. So this is, so now just to know where the exchange term comes from, if you have the repulsive and the attractive potential, which are asymptotically degenerate, then the difference between these two will give you the exchange exchange energy. Okay, and this is something. So now let me identify. So whatever I told you so far is generic. It should happen for every single electron system with a core, which are identical. Now, now we have to focus down on one particular thing, and we are migrating to lithium. So lithium is what we are doing, and here is so instead, so what we advocate is that if one has to do this, discuss this carefully at the ultra cold temperatures, which is where the experiments are now going, we have to look in terms of the total cross section, which was measured, which was kind of discussed earlier, rather than the elastic and charge exchange giving you a total cross section. And and you can see that there are differences between what you would calculate in as a total cross section as an incoherent sum of the charge exchange and the elastic, whereas if you take in all the interference terms, you get another value of cross sections. The differences are not that major, but they are significant. But it's not just about small differences. There's a consistency issue. So if you now think in terms of diffusion, which is the act of how a particle will travel in a cloud of gas. And if you're looking at diffusion, then diffusion cross-section, the diffusion cross-section of such an ion in a cloud of cold atoms is going to be basically is this, which is essentially the loss of forward momentum. Okay, and in this formalism, the diffusion cross-section is equal to the total cross-section in the S-wave limit. Okay, because the cosine theta goes because it's spherically symmetric, and this is an identical equation. I mean, this is completely valid. Now, what happens is in literature, there's a tendency for people to say twice charge exchange, okay, is equal to the diffusion cross section. And if you, so for instance, when you compute it for lithium 6 and lithium 7, what you find is that for lithium 7, this works very well, that the green and the blue curves are nicely going on top of each other. However, for lithium 6, this breaks down completely. So, and then, so there are ad hoc prescriptions which need to be used, but in order to correct for what is the total cross section, etc. So I will just, I have to move fast. So, okay, so if you do diffusion by collisions, this is the diffusion cross, diffusion, this is the diffusion cross section. And so let me now just move on to the other part. And if you want to look at collision rate coefficients, so this is the rate coefficient, you can then compute it for the old and the new things. And you can see at low temperatures, this stuff starts mattering. Now, one of our prime motivators from long ago was this charge hopping conductivity paper by Robin Cote. And a lot of this work, which I just described, came from actually examining whether all this stuff locks in properly. So we went into archaeological expedition from 1933. And so here's the thing. So diffusion by hopping, what do I mean? So essentially there is, let's assume, so here's the problem. The problem is, let's take a single ion, and we have heard several variants of this. Let's take a cloud of cold atoms, and within the cloud of cold atoms, you put a single ion, and you ask the following question. Where is the ion going to be as a function of time? As a function of time, okay? And of course, there's going to be diffusion due to collisions. However, and in most of the ion atom cases where there are heteronuclear ion atom species, this is fine. But when you are in a homonuclear situation, there is a difference. And the difference is that, and you are very cold, you have the wave packets, which are the delocalized wave packets of the ions and the ions of the ion, with a lot of delocalized wave packets of the atoms, which are cold. And there is this probability of overlap. And given that the probability of overlap exists, the probability of hopping between the of an electron from an atom to the ion exists. And that leads to the hopping mobility that you have, that Robin Cote described. So we have now done a specific calculation for lithium in 3 dimensions with the intention of actually going to the lab and trying to observe all this stuff. So basically so you have a characteristic de Broglie wave packet for the ion and the atom, and we've assumed that the ion and the atom are threshold ionized like they do in Stuttgart. You can actually have a single ion which is at the temperature of the atom. So, and then you start doing, this ion starts interacting with the gas around it via collisions and hopping. So now what can happen is, so let's go to this. So essentially, when you hop, there is no change in the, or little change in the mass distribution, but the charge shifts. Okay, that's the big that's the big difference between these two. And essentially, what can happen? And here we look at only hopping. You don't even have to hop to the nearest neighbor. You can be to the next nearest neighbor, or you can be beyond. It's a question of probabilities of overlap and what is the number density at a particular distance in a shell around this particular ion. So that is where we are. And so essentially what you have is the probability of ion atom overlap, exchange energy, integrated over the distribution of the atoms surrounding the ions. And this is what tells you, I mean, so all of the atoms are courting the ion to give the electron, and one of them manages in a given time. And let's not, I'm just kind of running out of time, so just to make a point. So now what you can do is the following. You can compare for the lithium system, the difference between collisional transport of the ion and the hopping. And you can compare the rates, and you'll find that the hopping rates are up here, okay? And these are three at different densities. These three curves are at different densities, N1, N2, N3. But the hopping rates are here. The collisional rate coefficient is here, okay? So you can see that there is a region of space at the ultra cold regime where hopping can really dominate you. However, this is not the full story, because one has to also realize something very important, which is that collisional diffusion goes as the inverse of the number density of atoms which surround you. Hopping diffusion goes as the number density of atoms that surround you. So obviously, if the environment around you is more dense, the chance of hop increases, whereas you are going to diffuse to much larger distances if your density goes down, and collisional mechanism is the only one which is operational. So these are two competing mechanisms, and that leads us to something. So essentially, the problem, once again, restating it, you start with an ion in a density a cloud of atoms here, okay, and then it goes there. So it started here and it ended up there. And this is what we want to find. Where does the ion land up in after a certain time? Now, the really funky thing here is the following. If you look at diffusion because of collisions, it's this orange or red line that you have here. At the origin, it is low because there's large density, and then the density goes down, and you diffuse, the diffusion coefficient increases. For hopping, the density, the hopping diffusion is very high at the beginning. It drops down, goes below zero, and then goes back up again to zero, because hopping requires a density distribution. So now when you look at the combination, so diffusion is one object. It will be the incoherent sum, in this case, of hopping and collisions. And so what is happening is that, let's say we start with an ion at the origin. It is going to diffuse out, okay? And if there is no hopping, it is going to continue to diffuse out, and we will have a certain residence time in the system, after which the ion is gone. If there is hopping, then it will diffuse out, it will go somewhere here, but now the direction of diffusion has changed. It's going to go back in. If you start anywhere, if hopping diffusion is a valid mechanism, if you start anywhere below 2.5 on the radial distance, you will locate on the average, the ion will be located in a spherical shell, okay? In the spherical distribution of atoms, in the spherical shell, it'll be located at a shell of a particular radius. And that is a very clear experimental signature to look for. And that will be, so essentially what that means is the following. So how the diffusion happens is essentially, so if you have an ion which is created at the origin, here is the ion moving ballistically. The blue lines, the blue points are the hopping diffusion. The collisional diffusion is here. And essentially, you can see that there's superballistic hopping diffusion in the early stages where the density is extremely high, and then it kind of becomes subdiffusive, and so on. It also tolerates electric fields. So it also tolerates electric fields. So we have done simulations in the presence of DC electric fields. And at this level, it works. There is a certain ion hold time, which is in very controlled situations of the order of a few milliseconds, okay? And it kind of then shrinks if your electric field control is a bit poorer. And I mean, this is kind of, so we have looked at the Stuttgart experiment with this ion, and we have done the numbers. And our conclusion was that the experiment at Stuttgart was not in the range of this thing because it's rubidium. Okay, and rubidium, the numbers change for rubidium significantly. So I think I just answered a question which would have come. So anyway, so I'm taking 2 minutes from the question time. But okay, so now we have a lithium experiment, okay, which we are building. We have like lithium 6 and lithium 7 at a few hundred microkelvin temperatures. We are pushing to go lower and build up densities. And we have our own version of a time of flight with a kind of resolution, not the Starship Enterprise kind of resolution that the Stuttgart experiment has, but we still call it the dilithium experiment because why not, and what else? And so that is essentially where I would kind of leave you with, and that's the end. And yeah, that's the end. So
well, thank you very much, Sadiq. We have time for 1 or 2 questions.
So thank you for the wonderful talk. And we have also done the numbers regarding the charge hopping. So I agree that in rubidium experiment, there was no prospect to see it. But I have a more basic question, because I'm always confused by this separation of 2 mechanisms of charge hopping and the charge exchange. So, because if it's, in my view, if I consider 2 partially overlapping wave packets, I can translate it to the scattering theory language, just get different contributions from the plane waves, and I would be able to just use the potentials to calculate the resulting charge exchange process. But in the paper of Raman, it is somehow well separated. So I would like you to comment on that, because you seem to have done
right. So we analyzed. So the well-separated picture of Robin-Cote needs to be revised. Okay, so that is not something that. So Robin is up next, so I will kind of shove that question to him. The thing that I would answer, which is actually a very important question, is, and I suspect Johannes is going to ask me the same question, which is the difference between charge exchange in a collision and the hopping, and which is what you asked, right? Yeah. So the thing is the following. So if you are looking at collision theory, okay, what you are doing is you have an ion, you have an atom, and you are doing a 2-body interaction, which is where these 2 bodies are in a universe of their own, all right? What is happening here, in some sense, is that you are in an environment. And that environment is continuously talking to this atom. I mean, I'm giving you a very loose thing. We can sit down and we can really, but there's an environment of atoms. And why just these 2? The atom, the gas is dilute enough not to start, and the timescales are small enough that nothing starts moving in a collisional state. Okay, so the question you ask is, why just 2, 1 identified atom and 1 ion? So then I can, if you want to take it to a collisional framework, you can say that the ion is exercising free choice of, actually shaking hands with its environment. And but the question is, how do you write that state? And that is actually where I want to really take this forward with a much more, um, let's say, meaningful, many body way of doing things. We are humble experimentalists at the end of the day. I mean, not Olivier and not Robin. And not Robin, but the fact is, yeah. I mean, our origins are, at least at Bangalore, our origins are, yeah. So, so the thing is that we have to start somewhere. This is where we started, and you know, there have been a series of talks on many body effects of ions in atoms. By the way, so I will tell you this for the many body things. If there were two ions, they would locate on this spherical shell. If this whole paradigm works as we imagine it to, then they would locate themselves on opposite sides of the shell, because the electric field interaction between these two ions is significantly lower than what that what the stray fields that we have computed this thing for. So, you know, we could actually start seeing some organization of ions, just ions. I mean, so this is where we are.
Okay, so thank you very much, Sadiq. In the interest of time, we'll move on to the next talk.